Right. So we've had a look at the mass spectrum of a molecule that has lone pairs of electrons. And so when the electron impact happens, we know that it's likely to lose one of the lone pairs of electrons. What about if we look at a molecule that has no lone pairs of electrons? And so the molecule I'm interested in is pentene. It doesn't have lone pairs of electrons, but it has pi electrons. And so what we want to explain in this is I'm interested particularly in this peak at 41. Of course, look out for the base peak, which should be apparent, and look out for the molecular ion, which you can easily calculate from the molecular formula. So see if you can see those on the spectrum. But to explain the peak we see at 41, let's have a look at what happens first with pentene. Here's pentene. What happens when it gets bombarded with a high energy electron? Well, that high energy electron is going to knock off an electron from the molecule, and we'll end up with two electrons in the end, and we'll end up with a radical cation on the other end. But which electron do we lose? We don't lose any lone pairs because there are no lone pairs on pentene. What we're going to do is we're going to lose one of the pi electrons, and that's what I've shown over here. So you see that this pair of electrons we've got here, I've taken away one of those electrons, it's been knocked off, and only one of the pi electrons remains. But of course, if you knock off an electron, you're left with a positive charge. Now, this here is your molecular ion, and that's what you will see in the mass spectrum. So the question is, how is this going to fragment? And it's quite interesting, and you need to practice this mechanism because the bond beta to this is what's going to cleave. So what we can do is we can take this unpaired electron and move it one bond along, and from this pair of electrons we can find another electron to pair with it. So you'll get an electron coming from this side, electron coming from this side, to form an extra bond over here. So we'll end up with a double bond. But what's the downside of it is that we've used up all of this bond. We take the other electron from this bond and it's going to go to the atom nearest it. So you can see that on this side the CH3 fragment receives that electron. This of course is neutral. There's no movement of charge when you use these half arrows, when you use the fishhook arrows, and so this is uncharged and will not be observed in the mass spectrum. Of course, where does the positive charge go? The positive charge is going to go to the CH2 over here. You'll see that this has 4 bonds attached, no charge attached, and you've got a double bond on the side. So you've got an allyl cation. You've got an allylic carbocation over here. And what's interesting about this carbocation that's formed is, firstly, its mass is 41 and its charge is 1, so we see it in the mass spectrum, M over Z of 41. But it's very easy to draw full arrows with these allylic carbocation. We can move the pi system onto that side, which will move the positive charge to the other side of a molecule, and so you can see that through this mechanism the allylic carbocation is stabilized. The positive charge is spread out through both ends of the molecule, and there are 2 resonance forms we can draw, and that's why this is formed as well. So it is resonance stabilized and it has M over Z of 41. So this explains how we can see M over Z of 41 in the mass spectrum.